Good day. Today's topic is kernel functions in support vector mechanisms. So kernelized support vector machines. So kernel function is a method used to take data as input and transform it into the required form of processing data. It computes how similar two points look after being projected into a higher feature space without ever performing the projections. So here these two are the linear separable example and not linear separable. So in the linear separable, we have an hyperplane dividing two set of class data sets, class 1 data sets and class 2 data sets. Like you can see, one is in red color and another one class data sets in green color, which are separated by a hyperplane, which is a linear hyperplane. And when you see the non-linear separable, so it is all mixed together, like one class data set is surrounded by the other class data sets. So when you talk about the kernel, when it comes to non-linear, we use the kernel and we project one particular data set in one plane and other data set in the another plane. Say like it will be from 2D to 3D. We will be projecting it into the 3D. So kernel in SVM, some of the ideas behind kernels in SVM are similarity measurement. Uh, in this, kernels calculate how closely two data points are related in feature space. Dimensional expansion, they map data into higher dimensions implicitly without expensive computation. Flexible boundaries, they enable the model to draw curved or irregular separations lines, efficient computation, they avoid manually engineering additional features columns. Uh, Next is inner product trick, which is kernels compute complex features interactions using simple mathematical shortcuts. So using kernel functions, how do you use it? So some of the reasons to use kernel functions are nonlinear patterns. Many real-world problems cannot be separated with straight lines. Smooth separation, kernels allow boundaries that curve around data clusters. Reduced feature work, they eliminate manual creation of polynomial or cross terms. Improved accuracy, non-linear transformations capture deeper relationships, general adaptability. Kernels make SVM work well across diverse data types. Mathematically SVM kernel function can be represented by k of x comma x dash, which is equal to theta of x power t into theta of x dash. X and x dash, two feature vectors, theta of dot mapping function to higher dimensional space, theta of x power t and theta of x power x dash, dot product measuring similarity after mapping. So k of x comma x dash is kernel similarity scope. Instead of computing theta of x explicitly, which can be expensive, we can compute the similarity directly using k, which is faster. This is called the kernel trick. Linear kernel measures similarity using a simple dot product, best for linearly separable data with fast computation. Formula is something like k of x comma x dash, and where x comma x dash are feature vectors, and x power t into x dash similarity between the two properties. So next is the characteristics. Dot product similarity. It evaluates similarity using a straightforward dot product between feature vectors and straight boundaries. It works best when the data is linearly separable. Fast training, it trains faster compared to the more complex kernels. Sparse features, it is commonly used for text or document classification tasks. Wide margins, it produces boundaries that remain clean and interpretable. Polynomial kernel. So, what is polynomial kernel? Captures more complex relationships by raising features interactions to a power, allowing curved decision boundaries. Formulas are given by k of x comma x dash equal to x power t into x dash plus r the whole power d, where x power t and x dash dot product similarity and r is bias term and d is degree of polynomial. And characteristics of polynomial kernel is feature interactions. It represents combination of original features up to date up to a selected power. Degree control, higher degrees create more twists and turns in the decision boundary. Smooth curvature, it handles patterns that bend gently across feature space. Overfitting risk, improper degree settings may cause the model to memorize noise. Adjustable shape coefficiently allow fine-grained boundary customization. So next is RBF or Gaussian kernel. Maps data into infinite dimensions and works well when class boundaries are highly nonlinear and irregular. And its formula is given by k of x comma x dash is equal to exp, so exponential of minus chi square modular x minus x dash module the whole square, which is exp is an exponential curve function, and psi is controls how for influence of a point spreads, and mod of x minus x dash the whole square, square distance between the points. And characteristics of the RBF Gaussian kernel is distance based similarity. Closer points are treated as more like alike, forming tight clusters. Flexible curves, it adapts to boundaries that wrap and spiral around complex shapes. Gamma influence, higher gamma values make the decision boundary more sensitive. Default choice, it performs well when data complexity is unknown. Smooth output, it constructs continuous and visually appealing separation surfaces. And sigmoid kernel behaves like a neural network activation function, useful for problems with smooth threshold behavior. Formula k of x comma x dash is equal to tan h of uh, psi x power t x dash plus r, where tan h is hyperbolic tangent and psi is slope control, and x power t and x dot is x dash is dot product similarity, r is bias or shift terms. So, characteristics of the sigmoid kernel are neural inspired output. It resembles activation behavior found in neural networks. Hyperbolic tangent, it applies a tan H based transformation to input pairs. Parameter sensitivity, it requires careful tuning to avoid unreliable results. And specialized use, it is helpful for modeling data with neural like distribution. Non-guaranteed validity, it may not always satisfy mathematical kernel conditions. Custom kernel, yeah, user-defined similarity, a function designed to incorporate domain-specific knowledge when standard kernels are insufficient. Formula k of x comma x dash is equal to exponential of uh, minus psi square mod of f of x minus f of x dash mod whole square. F of x custom feature transformation, and psi is sensitivity to feature differences, and dot mod distance metric between transformed points. And characteristics of custom kernel or domain tailor allows designing similarity measures specific to specialized datasets or expert knowledge. Flexible feature mapping can use handcrafted transformations, learned representations, or hybrid metrics. Custom distance metrics like supports non-Euclidean measures like cosine, correlation, and Hamming. Better accuracy for unique data works well when standard kernels fail to capture real patterns. Complexity trade-off may require mathematical checks to ensure SVM compatibility. Choosing right kernel, some of the scenarios for choosing right kernel or linear data use the linear kernel when boundaries remain straight and wide. Curved trends select the polynomial kernel to capture mild curvature. Complex shapes prefer the RBF kernel for spiraling or circular behavior. Neural similarity experiment with the sigmoid kernel for activations like effects. Unknown patterns start with RBF when the data shape is unknown. And tuning kernel performance, some of the techniques for tuning kernel performance are grid search, parameters combinations are tested systematically for best accuracy, cross validation data is split repeatedly to check generalization strength, regularization control, penalty settings prevent of overfitting in complex spaces, gamma adjustment distance sensitivity is tuned for local or global effects, degree refinement polynomial complexity is adjusted for smoothness, and applications, some of the applications of SVM kernels are image recognition. Kernels detect textures, edges, and fine visual variations, making them useful for classifying objects and visual patterns. Text classification, linear kernels handle sparse language features efficiently, helping categorize documents, emails, and sentiment-based text. Medical diagnosis, RBF kernels identify subtle biological irregularities that may indicate disease, supporting early detection and classification, traffic anomaly detection kernels highlight suspicious network behavior, helping cybersecurity systems identify unauthorized access patterns, financial fraud analysis kernel boundaries expose unusual payment clusters and transactions behavior, assisting fraud detection systems. Advantages, some of the advantages of using SVM kernels are nonlinear handling. They allow the model to learn from complex data patterns that cannot be separated by straight lines, enabling more accurate classification boundaries. Feature flexibility, they reduce the need for manually crafted features. Transformations, since kernels implicitly create richer dimensional representations. Noise resistance, they perform well in moderately noisy environments, helping the model remain stable even when data contains irregularities. Smooth boundaries, they generate visually consistent separation surfaces that curve naturally around data clusters and reduce jagged decision lines. Domain versatility, they work across text, images, signals, and medical data, making them suitable for a wide range of machine learning applications. That's it about the kernelized support vector machines. So I'll show you the implementation of the kernelized support vector machine. So you can see we are using the SkyKit SKLM. So these are the libraries that we import, and also we are using the breast cancer data sets, and also we are using the matplotlib because the output will be a plotted graph. And here we are loading the data and select two features for visualization. So which is X cancer data and cancer target. Use only the first two features of the breast cancer thing. And create and train the SVM model with the linear kernel. And here we are using C1 is equal to C is equal to 1 provides a balance between the margin width and the misclassifications. So this is where the we defining C is equal to 0. And the kernel is linear one, and SVM model, SVC kernel, and we are inputting. SVM model, we are fitting between these two data sets, X and Y. And visualizing the decision boundary. Decision boundary displays from the estimator, SVM model, and we're calling X. And response in this code method predict and alpha is equal to zero point 0.6. That is the transparency of the decision regions. And C map is equal to cool warm, the color map for the regions. X label equal to cancer dot feature name 0, and Y label is cancer dot feature name 1. And scatter plot, we will be getting the output as a scatter plot for the actual data points. Here, plot dot plt dot scatter is plot dot scatter x, the first column, and we'll be here calling the x column dot comma 1. C is equal to y, S is equal to 30, and H color is K, Z map is cool warm, and plot title SVM patient boundary on breast cancer data, So plot show. So now we will be running this code, executing this code. So you can see the output. So this is how the mean texture and mean radius we have found in the breast cancer data. So you can find the red dots and blue dots all being altered. But we'll have the hyperplane in between them to segregate or differentiate between the two data sets, two classes of data. So here we will be having the blue dots, and some blue dots will also appear, which is all outliers. We'll ignore that. And major of the class data sets, class 1 and class 2, we will separate. You can see the differentiation between the gray, cool warm colors and the blue color here. So that's it from the SVM implementation, the kernel is